All right, friends, let's take a look at Unit 16. This is the third installment of reaction kinetics. If you're following me in the Zoomed-All book, this is 12.3, determining the form of the rate law. So we talked about last time the reaction mechanism, and we said that the reaction mechanism was a series of steps which occurs that outlines the precise manner in which reactants become products, right? And we said that the rate law is going to help us to determine exactly what that reaction mechanism is. So let's take a look at one method for writing the rate law or determining the rate law, and we call that the method of initial rate. Okay, the method of initial rates. So we've got a chemical reaction here. This is NH4 plus aqueous plus NO2 aqueous yields nitrogen gas and 2 moles of H2O liquid. Now, first of all, let's remind ourselves that only reactants count. Products do not count in this type of a chemical reaction or determining the rate law in this kind of a chemical reaction, because again, if we consider the backward reaction, things get very, very complicated very quickly. So we'll just study the reaction when the reaction simply begins. In other words, the initial reaction. So let's take a look at table 12.4. This is the initial rates from, these are the initial rates from 3 experiments for the reaction of NH4 plus NO2 minus yielding N2 and 2H2O. So we've got 3 different experiments: experiment 1, experiment 2, and experiment 3. And the type of data that we have are concentrations of both the reactants, the NH4 plus and the NO2 minus, and the initial rates for those types of reactions. All right. So, for example, in the first experiment, we have an initial concentration of 0.100 molar NH4 plus and an initial concentration of NO2 minus of 0.0050 molar. For that combination, we get an initial rate of 1.35 times 10 to the minus 7th. And remember that rate is measured in moles per liter per second, or in other words, concentration per second. So it's 1.35 times 10 to the minus 7, and we have a second experiment and a third experiment respectively. Now, how do we use this information to determine or help us to determine the rate law? So recall that the general form of the rate law was this. The rate was equal to some constant, and we'll have to determine what that constant is, times the concentration of the reactants, in this case the NH4 plus and the NO2 minus, and those are both set to some exponents. We'll call them N and M. So the first question we want to know is, how do we determine the value of the exponents? How do we determine the N and the M? So here's how we do it. We look at the various experiments. I want you to look at just experiments 1 and 2 to start with, just those 2 experiments. I want you to notice that the NH4 component, the NH4 concentration remains constant, right? The NH4 concentration remains at 0.100 molar for both of those reactions, right? For both of those experiments. Now, the initial concentration of the NO2 minus is going from 0.0050 to 0.10. That represents a doubling of concentration, right? A doubling of concentration. Now let's look at the initial rates. If we look at the initial rate difference in these 2 experiments, as the NH4 plus concentration remains constant, when the initial concentration of NO2 minus is doubled, look what happens to the rate. The rate, 1.35 times 10 to the minus 7, becomes 2.70 times 10 to the minus 7. That is a doubling of the initial rate. So let's take a look at what happened. The initial concentration of the NH4 remained constant. So this one, the NH4 plus 1, remained constant. But the other one, the NO2 minus 1, was doubled. And when that happened, what happened was that the rate also doubled. Now let's take a look at the parts other than the NO2 minus. The K, well, that's a constant. That's not going to change, so that's a constant. And we now know that NH4 plus is constant between these 2 experiments anyway. The NH4 plus is also a constant. That means that if the concentration of NO2 doubling produces an initial rate doubling, then M must have been what? 2 to the what power is equal to 2? Well, simple. 2 to the first power is equal to 2. That means that the NO2 minus exponent must be 1. All right? Let's go through that argument one more time. We've got three experiments actually, but we're going to focus on the first two because in these first two, what's going to happen is that the concentration of NH4 plus remains constant. So we hold that constant so that it doesn't play into the rate. On the other hand, the initial concentration of the NO2 from experiment 1 to 2 doubles. That causes a doubling of the initial rate. So if the NH4 plus concentration is remaining constant, and of course K is a constant as well, that must mean that if we double the NO2 minus concentration, which we did, we took it from 0.050 to 0.050 to 0.010, then the number, the exponent which produces a doubling of rate must be 1 because 2 to the first power is equal to 2, and we've determined now the exponent for the NO2. Okay, fair enough. Now what we want to do is let me erase this, and now let's look at two different experiments. We're going to look this time at experiments 2 and 3. I want you to notice this time when we compare these two that the initial concentration of the NO2 minus is remaining constant. But the initial concentration of the NH4 plus is doubling, right? We're going from 0.100 to 0.200, so that's a doubling of concentration. Well, let's take a look at what happens to the initial rate when we double the concentration. We're going from 2.70 times 10 to the minus 7 to 5.40 times 10 to the minus 7. That's double, right? That's also double. So that means that when if we hold the NO2 minus 1 concentration constant, it's no longer affecting the rate, right? It's no longer affecting the rate. Now, and K, of course, is not affecting the rate. It's a constant. So the important factor here that's affecting the rate is the NH4 plus 1. When we double that, we double the rate. That means, just like for the NO2 minus, that the N must have been 1 as well, right? So we've now determined the exponents for both the NH4 plus 1 and the NO2 minus 1. They are simply 1 and 1 respectively, all right? All right, now let's move on. We're not quite done. We have to determine the value of K, right? So just because we determined the exponents doesn't mean that we've determined the entire rate law, right? The rate law includes both the exponents and the value of K. So what we're going to do is we're going to determine the value of K by doing this. We're going to say that K is equal to, we're going to go back to this equation. And now that we know that the N is a 1 and the NH4 plus has an exponent of plus 1 and the NO2 minus has an exponent of plus 1, now what we're going to do is go back into the table. We're going to use the first trial, the 0.100 molar for the NH4 plus and the 0.0050 for the NO2 minus, and the initial rate for those two concentrations is 1.35. So we're simply going to plug in rate is equal to 1.35 times 10 to the minus 7, which is equal to K times NH4 plus 1 to the first power, NO2 minus 1 to the first power, and that's how we'll determine the value of K. K then is equal to, now we'll divide 1.35 to the 10 to the minus 7th. That was moles per liter per second. That's the unit for rate, divided by the concentration of 0.100 moles per liter. That's the concentration of one of the reactants times the concentration of the other reactant is 0.0050 moles per liter. And we get this number, 2.7 times 10 to the minus 4 Now let's take a look at the units that we're going to get. It's liters per mole per second. Liters per mole per second. Now, I'm going to talk about the units for K in just a few minutes, but you can derive these units by cancellation of what you have here, right? So here we have moles cancels with moles, and I'm left with one more mole left. That's the moles that is on bottom. Seconds doesn't cancel with anything. We see it again right here. And liters, this liter cancels with this liter, and I'm left with one more liter. So you can convince yourself that the unit for K is liters per mole per second, but I'll show you an easier way in just a few minutes. So now let's complete the rate law. The rate law describes the rate of this reaction at this temperature for any concentration of this combination of reactants without having to actually do the experiment. So here it is. The rate law can be written as rate is equal to K, which is 2.7 times 10 to the minus 4, that's what we just calculated, is liters per mole per second, times the concentration of NH4 plus to the first power, times the concentration of NO2 minus 1 to the first power. With this rate law, I can now calculate the rate in moles per liter per second for any combination of NH4 plus 1 and NO2 minus 1 that you give me, right? Now remember that this K is temperature dependent, so it has to be at that temperature. The K is 2.7 times 10 to the minus 4 liters per mole per second, but it has to be specifically at that temperature. Now I told you I talked a little bit about the units for K, and so let me do that now. Remember that the units for rate have got to be moles per liter per unit time. Almost always the unit time is going to be seconds. So we'll make it seconds this time. Moles per liter per second, that was what was given to us in the table. That was the initial rates unit. So moles per liter per second is equal to, now notice that we have a concentration times a concentration. A concentration is moles per liter, and it's to the first power. And this concentration is moles per liter, and it's to the first power. That means that these two combinations, in multiplying together, we get mole square per liter squared. So the question is going to be, what do we have to make this unit for K so that we end up with a rate of moles per liter per second? This is what we're going to have to do. We're going to put liters on top. That's going to cancel with one of these liters on bottom, and that's going to leave me with this liters to the first power on bottom. Seconds is on the bottom because seconds has to end up on the bottom of the rate, and liters is going to, I'm going to have liters on top to cancel with one of these liters on bottom. So liters on the bottom is going to cancel, one of them is going to cancel with this liter on top. So that'll cancel, and I'm left with a unit for K of liters per mole per second. All right. One last thing, and that is the overall order of the reaction is this. The overall order of the reaction is the sum of the two orders that I've calculated for N and M. 1 plus 1 is 2. So the overall order for this reaction would be 2. So what have I accomplished in this section? I've used the law of initial rates because I was given data involving multiple experiments or multiple trials, right? And multiple initial rates. And I use that information to determine the exponents first, the N and the M, for the two reactants that I had. There might be one reactant, there might be two, there may be three. But in any case, what I'm going to do is I'm going to determine those exponents first. I'm going to plug those concentrations into one of the trials. It can be any one, but I almost always use the first trial. It's just the easiest one to use. I just remember to use the first one. I calculate K and I determine the unit for K, right? The unit for K. And the next thing I'm going to do is I'm going to determine the overall order. 1 plus 1 in this case is 2. If it had been 1 and 2, it would have been 3, and so forth. I'll write the overall rate law, and that will do it. I'll see you in the next one. Thanks. Bye-bye.